Bismillahirrahmanirrahim. Welcome to my channel Lodi Academy. In this video we will learn about approaches to SQL statement tuning in Oracle. We will discuss about the restructuring the indexes, restructuring the statement, modifying or disabling triggers. These are the sections by which you can improve SQL statement efficiency. Restructuring the indexes is a good starting point because it has more impact on the application than does restructuring the statement or the data. Remove non-selective indexes to speed the DML. Index performance critical access paths. Consider hash clusters but watch uniqueness. Consider index clusters only if the cluster keys are similarly sized. How you can monitor indexes? To monitor the indexes, you have to run one command. Do not use indexes as an panacea. Application developers sometimes think that performance will improve if they write more indexes. If a single programmer creates an appropriate index, then this might indeed improve the application performance. However, if 50 programmers each create an index, then application performance will probably be hampered. So these are the commands you can see, that alter index, index name, monitoring usage. By this you can monitor the index, and then to stop the monitoring you have to run the same command with no monitoring usage. There are many dictionary views are available, like DBA indexes and other you can find in dictionary views. When you start monitoring usage, then you can view those dictionary views and you can find that this index is in use or no. We came back to restructuring the statement. Rewriting an inefficient SQL statement is often easier than repairing it. If you understand the purpose of a given statement, then you may be able to quickly and easily write a new statement that meets the requirement. Consider alternative SQL syntax. Because SQL is a flexible language, more than one SQL statement may meet the needs of your application. Although two SQL statements may produce the same result, Oracle may process one faster than the other. You can use the result of the explain plan statement to compare the execution plan and costs of the two statements and determine which is more efficient. This example will show the execution plan for two SQL statements that perform the same function. Both statements return all the departments in the department table that have no employees in the employee table. Each statement searches the employee table with the subquery. Assume there is an index on the department number column of the employee table. You can see the first statement and its explain plan. As you can see, the explain plan is showing that it is filtering and accessing full table access of department and full table access of employee. Select statement, you can see it is mentioning in the where clause department number, not in select department number from employee. So we are using here not in. Oracle performs full table scan for this query. definitely time consuming for huge data. Now we will see the output indicates the Oracle executes this statement by performing a full table scan of employee table despite the index on the department number column. This full table scan can be a time consuming operation. Oracle does not use the index because the subquery that searches the employee table doesn't have a where clause that makes the index available. I hope you understand, because as I mentioned earlier that index was available on the department number column of the employee table, not on the department table. So in the statement which is in subquery with employee table having no where clause, so index is not in action. However, the second statement, in second statement you can see it indicates that Oracle executes this statement by performing the same row by access. Second statement, as you can see, second statement is showing where not exists, and the subquery is having the where clause and it is having connection by the department number column with the parent query's department number column. So now you can see the explain plan, it is showing the where clause of the subquery refers to the department number column of the employee table. So the index department number index is used. The use of the index is reflected in the execution plan. The index range scan of department number index takes less time than the full scan of the employee table in the first statement. Furthermore, the first query performs one full scan of the employee table for every department number in the department table. For these reasons, the second SQL statement is faster than the first. If you have statement in your applications that use the not in operator as the first query, as in this example does, then you should consider rewriting them so that they use the not exist operator. This would allow such statement to use an index if not exists. Alternative SQL syntax is effective only with the rule-based optimizer. So this is very important tip actually, that stop using not in and replace it with not exists operator, so you can get faster results. Compose predicates using and equal sign. Use equijoin whenever possible. Without exception, statement that performs equijoins on untransformed column values are the easiest to tune. Choose an advantageous join order. Join order can have a significant effect on performance. The main objective of SQL tuning is to avoid performing unnecessary work to access rows that do not affect the result. This leads to three general rules. Avoid a full table scan if it is more efficient to get the required row through an index, rows or row. Avoid using an index that fetches, for example, 10,000 rows from the driving table if you could instead use another index that fetches 100 rows. Choose the join order so as to join fewer rows to tables later in the join order. Example, this select, you can see The where clause is showing column between, and then second table's column between, then third table's column with between, and then joins. You can see all the joins. Choose the driving table and driving index, if any. The first three conditions in the example above are filter conditions, applying to only a single table each. The least two conditions are join conditions. Filter conditions dominate the choice of driving table and index. In journal, the driving table should be the one containing the filter condition that eliminates the highest percentage of the table. Thus, if the range of A low to A high is narrow compared with the range of A call, but the ranges of B and C are relatively large, then TABA should be the table A, tab A should be the driving table. All else being equal, choose the right indexes. After you know your driving table, choose the most selective index available to drive into that table. Alternatively, choose a full table scan if that would be more efficient. From there, the joins should all happen through the join indexes. The indexes on the primary or foreign keys used to connect that table to an earlier table in the join tree. Rarely should you use the indexes on the non-join conditions except for the driving table. Thus, after tab A is chosen as the driving table, you should use the indexes on the B.key1 and C.key2 to drive into tab B and tab C respectively. Choose the best join order, driving to the best unused filters earliest. The work of the following join can be reduced by first joining to the table with the best still unused filter. Thus, if B call between is more restrictive, means rejects a higher percentage of the rows seen than C call between. The last join can be made easier with fewer rows if tab B is joined before tab C. Use untransformed column values. For example, use where A dot order number is equal to B dot order number rather than where to number substar A dot this and then instar and then. Means do not use SQL functions in predicate clause or where clause. The use of an aggregate function, especially in the subquery, often indicates that you could have held a derived value on a must record. Avoid mixed type expressions. Avoid mixed type expressions and beware of implicit type conversions. When you want to use an index on the watcher to column, for example, this charcoal column name, but the where clause looks like this, where clause a charcoal equals number expression. For example, variable here you are giving is a number. Oracle, when number expression is an expression of number type, for example 1, user environment session ID, comma num call, comma this type of, Oracle translates that expression into to number charcoal equals number expression. Because you gave number expression, so Oracle will convert this charcoal to number. This has the following consequences. Any expression using a column such a function having the column as its argument causes the optimizer to ignore the possibility of using an index on that column, even a unique index. If the system processes even a single row having charcoal column as a string of characters that does not translate to a number, then an error is returned. You can avoid this problem by replacing the top expression with the explicit conversion, like this, and charcoal equals 2 char of number expression. For example, if you have to give number expression, then do it with 2 char. It allows us of an index on number column because the default conversion is always character to number. This behavior, however, is subject to change. Making type conversions explicit also make it clear that character expression should always translate to a number. Write separate SQL statements for specific values. SQL is not a procedural language. Using one piece of SQL to do many different things is not a good idea. It usually results in a less than optimal result for each task. If you want SQL to accomplish different things, then write 2 different statements rather than writing one statement that will do different things depending on the parameter you give it. Optimization, determining the execution plan, takes place before the database knows what value will be substituted into the query. Execution plan should not therefore depend on what those values are. For example, you can see this select statement, select into table, and then where clause with between and decode and everything. Written as shown, the database cannot use an index on the sum column, it is a column name used there, sum column, because the expression involving that column uses the same column on both sides of the between. This is not a problem if there is some other highly selective indexable condition you can use to access the driving table. Often this is not the case. Frequently you may want to use an index on a condition like that shown, but need to know the value of variable LOVAL and so on in advance. With this information you can rule out the all case which should not use the index. If you want to use the index whenever real values are given for LOVAL and high-val variables, this is if you expect narrow ranges, even ranges where low-val often equals high-val, then you can rewrite the example in the following logically equivalent form. So now you can see the select statement. Change this half of union all if other half changes. Okay, now you can see this. You can see this. If you run explain plan on the new query, then you seem to get both the desirable and an undesirable execution plan. However, the first condition the database evaluates for either half of the union, all, is the combined condition on whether high-val and low-val are all. The database evaluates this condition before actually getting any rows from the execution plan for the part of the query. When the condition comes back false for one part of the union all query, that part is not evaluated further. Only the part of the execution plan that is optimum for the values provided is actually carried out, because the final conditions on high-val and low-val are granted to be mutually exclusive. Then only one half of the union all actually returns rows. The all in union all is logically valid because of this exclusivity. It allows the plan to be carried out without an expensive sort to rule out duplicate rows for the two halves of the query. You can use also hints to control access paths. Use optimizer hints such as ordered, full to control access paths. This is a better approach than using traditional techniques or tricks of the trade such as cust number plus 0, for example. So you can use like select and then you can mention slash star plus full, then table name in the brackets, star and backslash, and then you can mention the column names and from table and where clause rather than in a simple way. Use care when using in and not in with the subquery. Remember that where not exists is a useful alternative. Not exists is not only equivalent to not in, is not always equivalent to not in. Use with care when embedding data values lists in applications. Data value lists are generally a sign that an entity is missing. For example, you can see that where transport in mention the vehicle names. The real objective in the where clause above is to determine whether the mode of the transport is automobile and not to identify a particular make. A reference table should be available in which transport type equals automobile. Minimize the use of distinct. Distinct always creates a sort. All the data must be instantiated before your results can be returned. Modifying or disabling triggers. It's actually a very simple thing that using triggers consumes system resources. If you have more triggers, definitely insertion will take more time, updation will take more time. For example, when you are inserting and you are having some before insert, after insert triggers on the table, and those triggers are on the basis of your insert or update, they are changing the values in other tables which have other impacts, and if those tables are busy, somehow they are getting locked by some other user. So it will take time. Even this time will be in milliseconds, but if your transaction level is high in the real production environments, when transaction level goes very high, this milliseconds impact will goes to minutes, to seconds, to minutes, and then this load will go to the server level on the CPUs and the RAM. This is other thing, any other level of performance tuning then. So must understand this, that too many triggers adversely affect the performance of the SQL. And later on, if it is for example, if you say no, this is the requirement, we have to do this, okay, do that, but with proper care and proper study. Better thing is on insertion and update, try not to have many triggers. 1 or 2 or 3 triggers is fine. Those are also depends on what is written in the triggers. Thank you for listening. Hopefully this is helpful for you to understand, and we will meet again in the next video. Till then, bye bye.